one more type of possibility. What if we have sp hybridization? Let's say carbon dioxide is a good example of this. CO2. And we're referring to, of course, the hybridization of the central atom. And in this case, we have 2 bonds, 0 lone pairs. Again, bonds is the same as, or when we're counting bonds, single, double, and triple bonds are all the same. They're just 2 bonds in this case, 2 total bonds. So that gives us 2 electron groups, 0 lone pairs. So there's nothing to cover up. We observe the relationship here. If we get rid of all the extra stuff, all the lone pairs and all the bonds, that's the same shape, right? OCO, 180 degrees is the relationship here, because again, these electron groups, the O double bonds, will orient themselves so they are as far apart as possible. And of course, they would be on the opposite ends of the carbon, 180 degrees. And so this is a linear electron geometry. And linear molecular geometry, because there are no lone pairs. The electron geometry and the molecular geometry are identical. Okay, let's do a practice problem with this before we end. I'll draw this molecule, and then we will look at a number of the atoms present and determine their molecular geometries. Because when we're talking about three-dimensional shapes of organic molecules, we really don't care what the electronic geometry is. We are mostly concerned with what is the actual three-dimensional shape of the molecule, and that will be, of course, the molecular geometry, discounting lone pairs. The lone pairs still affect things, but they don't give us the final shape. So if we look at this nitrogen here, it is sp3 hybridized, 4 electron groups, 4 groups, 1 H, 2 H's, 1 carbon nitrogen bond, and 1 lone pair. That's 4 electron groups. 1 lone pair, and that means we have tetrahedral electron geometry, and trigonal pyramidal molecular geometry. How about if we look at this carbon here? Hopefully you see 4 electron groups, and you should count 0 lone pairs. And that leads us to tetrahedral electronic and molecular geometry, so we'll just write molecular geometry. So understand that this carbon is arranged in a tetrahedral shape. It might be more better to give that bond the dark wedge, make this CH bond the dash, to better imply the three-dimensional tetrahedral shape of that carbon. How about this carbon here? I would count 1 CC bond, 1 CH bond, and 1 CC double bond. So 3 bonds, 0 lone pairs. If you remember our earlier discussion, 3 bonds implies trigonal planar electron geometry. And because there are 0 lone pairs, and it's the same as the molecular geometry. So we have trigonal planar electron geometry and molecular geometry for this carbon, and that means that this triangle that we can define here, the C, C, and H are all in the same plane, as well as this central carbon. They're all in the same plane. Let's look at one more atom. This O. I count 2 bonds to it, 2 CC bonds, 2 lone pairs. And so that's 4 electron groups. And that implies tetrahedral electron geometry. 2 lone pairs, though, implies bent molecular shape. Because remember, we cover up those lone pairs when we think about the shape, and you can see the shape here implied in this COC bond. That has about 107 degrees in that bond angle.